So Chuck, what's the temperature outside now?
According to AccuWeather or according to me? Because if it's according to me, damn, it's hot. That's the temperature.
No, go.
Okay, let me look.
Do your thing.
Okay,
what's the temperature?
right now it is 72 degrees.
72 degrees.
Right now.
Outside.
Outside.
Where?
Hoboken, New Jersey.
So it's 72 degrees in Hoboken.
In Hoboken, New Jersey. Right.
Where in Hoboken is it 72 degrees?
All of Hoboken.
How do you know?
Because Google's just told me.
Wait, so how do you know that there's one thermometer, wherever that thermometer is.
That's true.
And that's what it's telling you.
That's what
it's not using thousands of thermometers and taking an average over the total area of Hoboken. What is the area of Hoboken?
1 square mile.
So that's 1 mile by 1 mile.
1 mile, right.
So somewhere in there's a thermometer that gave you that temperature.
Correct.
Okay.
Yes.
And you don't know where that is.
Well, if it read 98.6, I would know exactly where it is.
So we don't care,
right,
where the thermometer is.
No.
Because fractions of a degree don't matter to us.
No.
Even a degree here and there don't matter to us.
What I can feel is what matters to me.
Right. And so we're okay. It's in the low 70s.
Right.
Unless you're completely nerded out, no one's going to come to you and say, could you be more precise?
Right.
It's 72 degrees. Could you be more precise? Oh, by the way, the entire universe is at a temperature that is the same in every direction to 1,000th of a degree. The cosmic microwave background has a temperature that is the same in that direction as it is in that direction. And we can't say that about the rooms we live in our home.
That is true.
Because there's a vent over there, there's a window over here, and there's a pipe over there.
Right.
There is a standard height above the ground where the National Weather Service records its temperatures.
Really?
Yes.
Okay.
And I don't remember what that height is. It's somewhere within the height of a person.
Right.
Why isn't it lower? Because you know what's heating the air? The sun is not heating the air. The sun is an intense source of visible light. The visible light is not absorbed by the atmosphere. How do you know this?
Because it comes through?
Yes, because you can see the sun. Okay? If our atmosphere absorbed visible light, you would not see the sun. Then it hits the ground. Where does the visible light go? It gets absorbed by Earth's surface. Earth's surface then re-radiates it into the air.
Okay.
But not as visible light.
But not as visible light.
You know how you know that? You turn out the lights, the ground disappears. At night, the ground is not glowing.
Right.
Okay?
Right.
All right. Glowing visibly.
Visibly.
But it is glowing in the infrared.
Gotcha.
Okay. So infrared light comes up. If you have infrared trapping molecules in the air.
Yes.
Such as
methane. Carbon, water
carbon.
Vapor.
Carbon would just be soot.
I said carbon dioxide.
No, carbon is like...
No, carbon is the black stuff that comes...
Is it diamonds in the atmosphere?
Right, no.
Diamonds are carbon too.
Carbon dioxide, which is the gas.
Right. People loosely, a little bit irresponsibly, just speak of carbon as a carbon footprint.
Which I just did, and I know so much better.
It's a little bit irresponsible because carbon is not itself an enemy.
I forgot who I was talking to.
Okay. So, in fact, methane has carbon in it.
Yes, it does.
It's CH4. Right. All right. And carbon dioxide has carbon in it.
Yes, it does.
It's CO2.
Right.
And water also absorbs infrared.
Right.
And it does that without carbon.
Without carbon.
Okay. And that warms the air. If the ground is responsible for heating the air, then the closer you get to the ground, the higher the temperature
it's going to get. Right.
Okay.
So now all we have to do to cool the Earth is just get rid of the ground. Global warming itself.
That'll work. You don't have a planet, but right. So you pick a height above the ground that we experience, and that's a nice, sensible place to put the thermometer. Okay?
I got you.
As you keep ascending, you are farther and farther away from the heat source of the atmosphere.
Okay.
You would then expect what to happen?
Nice and cool, man.
Cool.
Yeah.
Temperatures drop.
Right.
In the old days, before air conditioning, people who had the means would go to
higher elevations.
Higher elevations in the summertime.
Oh, there you go.
Where it was cooler.
Hey, we're headed to our place in the mountains.
In the Poconos.
Oh, dear, will you be joining us?
So temperature drops.
Right.
And like I said, if you pay attention to this when you're in an airplane, because lately airplanes give you all the data.
Yes.
Okay?
Yes.
And one of them is what the outside air temperature is.
Exactly.
It drops and drops and drops and drops and drops as you get higher and higher and higher. A common temperature you'll see is like 40 below zero. That's what's happening in the troposphere.
Nice. Now tell me what the troposphere is again.
It is where all of our weather comes from. And we fly just
Above?
near the top.
Near the
of the
top of it,
troposphere.
so we don't go above it. We on the top.
We can, but we don't. Some very high-flying craft, like the U-2,
Right.
that would go into the
Now, do we fly at
stratosphere.
the top of the troposphere because it's
If you're above all the clouds, why fly through clouds if you don't have to? It's less turbulent, and air is thinner, so there's less resistance to the movement of the plane.
Then why doesn't the plane fall out the sky, man?
It's going really fast. There's a buoyant force from the air that is there. By the way, but you make an important point. There's an altitude above which it would have to fly really, really, really fast to get enough air going below it to give it the lift.
Gotcha.
So the higher you go, the faster you have to travel to stay flying. So the SST, the Concorde SST, the first and only ever supersonic transport for commercial aviation, that was up at 45,000 feet, around there.
Right.
Currently, we fly in the 30,000, 35,000 feet.
Ladies and gentlemen, we've reached our cruising altitude of 37,000 feet, and quite frankly, I'm freaked out.
All right, where was I?
So we're in the
temperature's
troposphere,
dropping.
and we're at the top of the troposphere.
Temperature drops to like 50 below zero.
Okay.
50 to 60 below zero. Then we go to the stratosphere.
Okay.
Something interesting happens in the stratosphere.
Go ahead.
That's where a molecule of oxygen has 3 atoms instead of the normal 2. The O3 molecule, turns out, sees ultraviolet light and it absorbs it, takes it out of action.
Gotcha.
But where does the energy go?
Oh, that's so cool, though.
It's very cool.
That's why we're not dead. Thanks, O3.
You're not dying from skin cancer,
Exactly.
right? So the UV molecule is completely gone. The persistent absorption of ultraviolet light in the stratosphere causes the temperature to rise because the particles are now getting an injection of energy that gets manifested as the kinetic energy of the particles themselves. And we measure the average kinetic energy as temperature. So, stratosphere, the temperature rises.
Whoa.
Yep.
That's wild.
Here's an interesting fact. Because the stratosphere is warmer than the troposphere, because the stratosphere is heated by the UV absorbing O3 molecule,
right?
What happens to heated gas?
It expands.
It gets less dense and then rises. Okay?
Yeah.
What that means is the boundary between the troposphere and the stratosphere is completely stable. There is no urge for minus 60 degree air to rise.
It's almost like a ceiling that is created.
It is a thermodynamic ceiling above our troposphere. And that's why our weather never trickles. Okay. It's a lid.
That's so cool.
Containing basically all of our weather.
That's amazing. I love it.
That's why a volcano can pop through that.
Right.
It can pop through. But if it pops through and goes into the stratosphere, it's not coming out.
Right.
It's going to stay there.
And that's why it's circular.
That's why it's
all the way around.
Without falling out.
Without falling out.
Without falling out.
Dude, that is so crazy. I love it.
All right. So next, we get to the mesosphere.
All righty.
I like me some mesosphere. You know why?
Why?
The air is way thinner now, but it's enough air to matter to interplanetary particles that the Earth plows through in its orbit.
Interesting.
Enough air to make some action. Okay? We intersect these particles very fast, 20, 30 miles per second.
Pretty fast.
So fast that the impact of those particles with that atmosphere, even as thin as it is, slows down the particles. Where'd the kinetic energy go?
Well, it's got to be somewhere.
Got to be somewhere. So it renders the atmosphere aglow.
Oh.
And we get meteor showers.
Nice.
So the mesosphere is meteor showers.
That's pretty cool.
Isn't that kind of cool?
Nice.
That's where all that happens.
That's where that happens.
And it doesn't happen in the troposphere.
Right.
Because
well, once it gets down there, it's like...
oh, by the way, it can happen down there if it's big enough.
Right.
Big enough, it'll try to burn up. But if it's still some left over, it'll keep coming down.
And if it's even bigger, you lose a barn somewhere.
Or you lose your dinosaurs. Yes, okay. That's the mesosphere.
Very nice.
Okay, now we get to, what's next? The thermosphere. Now, the thermosphere is another layer that absorbs high energy light from the sun. It absorbs high energy UV and X-rays. The sun also gives off X-rays.
Wow.
That's a lot of energy there.
The sun is dangerous.
We say, oh, the sun is beautiful. Under our layers of atmosphere, it is.
Right.
Put your bare ass out in interplanetary space.
Right.
Kiss your ass goodbye.
You're just a cancer-ridden chicken bone, burnt to a crisp.
All right. So in that layer, because of this absorption, such as what happened in the stratosphere, the temperature rises again.
Right.
It rises so high, it can get thousands of degrees. Thousands.
That is wild.
Yes.
I gotta
Oh my gosh.
This is so much better than Wikipedia. Things are heating up.
Yes, yes.
This is insane.
The thermosphere can get to thousands of degrees.
Amazing.
Now, if I put you there, it's actually not as dangerous as it sounds.
Okay.
Because there's a particle here and a particle
so it's
there.
spread out.
It's really spread out.
Gotcha.
And the concept of temperature loses meaning.
Right.
The way we normally
think of it.
Right. Because temperature,
it's not an oven.
the gas molecules are hitting you all times, and they're taking energy from you or putting energy in you. If there's a molecule hits you here, and then there, and then there, it'll probably feel cold, even though the individual speeds are really high for those molecules.
Gotcha.
So that's the thermosphere. But you know what happens in the thermosphere?
Go ahead.
Not only does it absorb the high energy ultraviolet and the X-rays, that's where the buck stops with the solar wind.
Right.
And that's where aurora take place.
Look at that.
In the thermosphere. Because the particles hit oxygen molecules, nitrogen molecules, bumps up the energy of the electron.
Okay.
Okay. So it took the energy, the electron is sitting at a higher energy level, and then unlike people, atoms don't like remaining excited. So they spontaneously de-excite and send visible light in these shimmering curtains into the atmosphere that we see aurora. It's beautiful. One more layer. And
after the thermosphere.
I shouldn't even call it a layer.
Shouldn't even call it a layer. But there are some molecules up there.
It's the exosphere.
Okay. What's going on there?
Nothing. It's where the density of air from our atmosphere blends into the density of particles in interplanetary space. At which point you don't know which one you're...
I was going to say, how do you make that differentiation?
It's when the densities are about the same, and then you're done.
So
You're done with Earth's atmosphere at that point.
You have transitioned.
And where do we orbit our low Earth orbit objects? You know, the space station, the space shuttle. Well, not the space shuttle anymore. SpaceX, Crew Dragon, all of them. They all orbit sort of in the upper thermosphere. You may not know that we intermittently have to boost the space station. Why do we have to boost the orbit? Because especially the space station that's got all of these solar panels.
Because
there's still some air molecules there.
So you don't want all that slapping up against there.
Except it happens.
Right.
That decays the orbit.
Right.
So every time we send up another craft, if it's in the schedule, it'll use its engines to boost it because there's still air molecules there.
Gotcha.
When you get into the exosphere, you're far enough away, that would never happen. And that's why, surely you've seen video from the space station orbiting Earth at night, and you're looking horizontally into aurora.
Yeah.
I mean, they're still above the aurora.
They're still above the aurora.
But
it looks like it's like they're a boat on a lake.
Yes, and it's shimmering right there. So they're in that same layer of the atmosphere.
Nice.
And like I said, it's thousands of degrees, but the temperature doesn't really...
Well, the temperature has no meaning, as you said.
It has no
just
meaning.
because of the way it's dispersed.
Right.
That's crazy.
Yeah, so there it is.
I love it.
A little bit of our atmosphere, and we should love it more.
Yeah. Without a doubt, because the sun is trying to murder you.
And somewhere in there, the bottom of the thermosphere, that's where the atmospheric density becomes so thin, it no longer scatters blue light from the sun.
Gotcha.
So if you look up, there's no sky blue.
Right. Things are dark.
Daytime sky is dark.
Daytime sky is dark.
Daytime just means the sun is up. That doesn't mean the sky is glowing.
Right.
And so that happens at the bottom of the thermosphere.
Bottom of the thermosphere.
And that's the famous Kármán line.
Oh, okay.
That people try to get above that. And that's the official
and then
definition.
They're like, I'm in space now. No, you're not.
Yeah, they're actually in a layer of Earth's atmosphere.
You're still in a layer of Earth's atmosphere. You did not go to space. So.
They pay a lot of money. Retract that. Retract that.
Okay, so you almost went to space.
So by those measures, the only people who ever went to the exosphere have been the Apollo astronauts who went to the moon.
Right.
Yeah, because they left Earth.
Right.
And all molecules therein.
Everybody else, you wasted your money. You got suckered. You got suckered.
That's all I got.
That was great.
You cool with that?
I'm so cool with that.
So there it is. The profile of our atmosphere.
Profile of our atmosphere.
So you can't just find any random planet out there in pitch tent and think you're going to be. And by the way, people say, oh, how fortunate it is that we live on such a planet. No, we evolved under these conditions.
Right.
So of course it's going to perfectly match.
Right, exactly.
And maybe we'd have to evolve differently on another planet with different protections, whatever, but it's all working for us.
Very cool.
You got it. All right, it's been another explainer.
Always a pleasure.
Always good for it.
Always a pleasure.
All right, Neil deGrasse Tyson, as always, keep looking up.